case of reinforcement learning. So multiple different paradigms which are being there, and then we have talked about the environment and the agent and how they are going to interact between them. Basically, agent need to interact with this environment, and accordingly, environment gives some rewards and the next state depending upon the action that an agent is taking. And once we understand this, we understand that such a thing can actually be mathematically formulated using a well-defined setup that is actually being called as MDP. That's actually the Markov decision processes. And within that, if I give you such an environment and agent interaction, and then you can decide, you can see that you can come up with different episodes. If you know the complete dynamics of your MDP, then you can draft full episodes, and given such different big episodes, you can you can formulate this. You can come up with different episodes. In between, you can mute your mics. Then we have seen this card poll problem, and also Atari games problem, in which we see that what are objective, state, action, and rewards. And then for the formulation, we first discuss about this Markov property, which is like this. And then we understood that what is a Markov decision process, which is essentially these tuples. So if I say that MDP and its dynamics, which essentially mean that the states which are being there, the actions which are being there, the transition probability, which mean to say that if you know the state and the action, you can come up with the next state. Reward, in which also state and action is going to tell you that what is the immediate reward, and the discount function. So this is going to be the state and action, and you can get the next state or you can get the reward. State transition probability need to be somehow a priori fixed, or if it is not fixed, then somebody need to tell you that, if you need to figure out the full exact MDP. So the meaning of that MDP is that the transition probabilities, the transition probabilities. Then Markov process chain we have also seen, and this is actually the probability, which is transition probability, which is telling that for every S and A, what is going to be the next state. And we all understand that at any state, if you take an action, it is not the case that every time you are going to land up to the same state. It's actually a complete probability distribution, and that given S and A, what are different states in which you can go, and what are the corresponding probabilities. Immediate reward is going to tell you that ST and AT, and the corresponding what is going to be the reward for it. What we have seen is that this can actually be seen as a reward, and in that we have seen that if you reach up to a terminal state, that can actually be seen as an episode. And we are not interested into these individual rewards. There are two things over which RL don't rely on, or don't work or consider them, is that what is the reward till now that you have got. Suppose that if you are at state S3, it doesn't mean, we are not looking for whatever the rewards that you have achieved till now, R0, R1, and R2. We only are interested in that what you are going to get now. And the second thing is that as soon as I move forward in the time, how much amount of weight I wanted to give to my upcoming rewards. So probably you wanted to give more weight to this and exponentially less weight to them, because your future is, as we have seen, that the future is unpredictable, as well as we are using a procedure, the algorithm, or iteratively we are building the solution, so that whatever the intermediate solutions, they are not properly correct or exactly correct. Then we have seen that how we can come up with different episodes, and which is essentially very easy, that from different states, you just choose the initial state with certain probability, and then until you got your environment have not given you a properly a next terminal state, you keep on doing this thing. And what you are doing is that you need to take an action, But how that is going to be the the pi or the policy that we need to somehow understand. And this pi need to ensure that we are maximizing this. So the pi, which is actually the policy, has to be in such a way so that it should have to maximize my discounted cumulative future rewards. In fact, not the absolute value, but its expected value. And once you have got the given st and at, you have got, pi is going to tell that for each st what is the next state, and given both of these, you can find out that what is the rt and what is the st, given the dynamics of the your mdp. But how to take an action, that is actually the policy, and that is the whole thing that one should have to really understand, that being an agent, you need to come up with that what is going to be the policy. So the policy is something that will take a state and give you the corresponding action. In fact, it's going to give you the full probability distribution over all the action, all the possible action, which means that if you are at a state st, then what are the different actions that you can take and with what probability that you can take them. So that is why you can see that at given state, what is the action and what is its corresponding policy. So if that is the policy, then there has to be a goal of your MDP, and your policy need to somehow fulfill that goal. Policy need to fulfill your goal, and your goal of your MDP is every time going to be maximize the DCFRs, expected value of these DCFRs, and the policy, if you start with some policy, we want to come up with a policy which is the most optimal policy. And we'll talk about this or define this optimal policy much more formally. But exactly it means that at any state, if I take an action, and if it is with respect to the given pi astic, if you know this really pi astic, which means that at any state st, if you take an action, that is the best possible action, because if you have taken anything other than that, then your DCFRs are not going to be, expected values not maximizing. So how to get such a thing is one thing, and then we'll formally define that DCFR, and we all understand that it's going to be RT plus gamma time RT plus 1, then gamma square RT plus 2, and so on. Keep on doing that. So this is the formula for this. And for 0 and for 1, that is myopic and far-sighted. Why do you require? As we have said, that it's our future is uncertain, as well as there are few other things. One reason is that we are predicting using an inaccurate model, which is iteratively going to be refined. Okay, so till now we have seen, and now we have reached up to a place where we are going to talk about the grid world MDP. So in this, what this MDP actually says is that we are having a 3x4 grid, in which only 2 states are the terminal states and other remaining states are non-terminal states. So that's your different states that you can have. So in this 2D world, if I say, then you are having 12 different states. Here the number of states is also fixed, but most of the time number of states is not fixed. What are the actions that you can take is that you can go left, right, up and down. What is going to be the reward? Reward is going to be every time you take any action, a reward is going to be -1. So what this such type of reward is ensuring that if you maximize such a reward, which means that if you are starting from any state, you need to reach to a terminal state. That is our goal. But if your reward is -1, you need to maximize this value, which means that you need to minimize the number of steps that you need to take. So your actual problem of this grid world MDP is going to be that I am at any, so it's also written that starting from any randomly chosen block, reach to a terminal state in the least number of actions. So we need to formulate all of these in such a way so that we can solve such an objective. And now you can see that whole thing, all these things are actually nicely setting up into our one such an MDP. And once we figure out our MDP and the dynamics of our MDP, then we need to somehow come up with this pi that is going to tell you that how how one can take how one can take different actions at any state. So so the given 2D grid world MDP, we need to figure out some optimal policy that can maximize DCFRs out of all the policies. So there are going to be infinitely different or many policies. One of them can actually be being shown over here. That is nothing but randomly, completely random policy. That's why we have said that's a pi I. That's a completely random policy. What does this completely random policy mean? That irrespective of where I am, I don't bother about that. Where I am, I will move left, right, top, and bottom wherever I wanted to, with equal probability. So that's why you can see that that is a random policy, doesn't consider anything, moves in all possible direction in equal with equal probability. That's actually a visual realization of any policy. This is another policy. That's the second policy that you can see, which is actually saying that if you are here, then I'm moving here. If you are here, then I'm moving here. If you are here, then I should have to move over here. So if I am at state 3, then I'm going to take the action that is to my right. If I am here, then I'm going down. So here you see that this is actually a random policy. This is not a random policy. And what is the philosophy of such a policy? That is also being written, that for immediate neighbors, one should have to move in the direction that can take you to the terminal state. And for others, you are moving in the direction that can take you closest to one of such immediate neighboring states. So the point is that you can see that this is a policy by which you can always always initialize your actual the policy that you wanted to take, but you need an iterative process. You need an iterative process that can somehow build or refine, build over this and refine this policy iteratively to some other policy, maybe to some other policy, and at last probably you come up with a policy like this, which is roughly better than this. And you can say that, yeah, this policy is at least making sense of our problem itself. So how can we start from here and come over here? This is the thing we are trying to see, how we can refine and iterate over different policies. Okay, so so till now all the formulation is going on, and still we require some more formulation to understand. Then we can start about how can we solve such an MDP. And we are not going to solve normal or simple MDPs in which states are fixed. We are going to talk about the MDPs in which states are very large number of states are going to be there. So first of all, let us understand that what is the solution of an MDP. So if I give you MDP, the solution is some pi, but that may not be the optimal solution. So the optimal or the best possible solution of an MDP is actually being said as the optimal policy, that is pi-astic that we are looking for. And policy is nothing but how we are planning to move. And this is your policy, which is nothing but the mapping between the state to the action. So your pi-astic or the optimal policy mean that it doesn't matter that in whatever state, say STIM, at any time my agent may be at any state. If I know what is my pi-astic, that is my guiding star or my guide, so that is going to suggest that what is the action, say at that point of time, what is the best action that I need to take. And since it is pi-astic or the optimal behavior that we are looking for, it is guaranteed, it has to be guaranteed that if you take this action governing or using this policy, then the DCFRs are maximized. So out of all possible actions, you are going to choose an action, and using pi-astic, and pi-astic is defined in such a way so that the action that you have chosen is actually the best action so far that you can choose out of all the possible actions, given that you are at that ST state at that time T. Now, so as we all understand that we are not going to talk about the only the DCFRs, but the expected value of such DCFRs, because it's actually a probability distribution and a chaotic framework, and random processes are actually going to happen. So we are looking for the expected behavior or the expected DCFRs. And if you choose your STs using your pi astics, and then DCFRs are going to be maximized. The expected value of your DCFRs are actually going to be maximized. Let us see much more formally what does it mean. Pi astic is, so it is that argument or the maxima. So over all the policies that you can have, exploring over all the policies, you are maximizing that policy, basically maximizing this thing, and returning what? That policy which is maximizing the expected value of my DCFR. So we are maximizing what? Expected rewards. So expected value of my DCFRs, and you can see that DCFR with respect to that policy. So iteratively over all the all the available policy, if you see that given some policy, if I find out that if I choose that policy, move accordingly, get myself terminated, got an episode, find out its discounted cumulative future reward, and find out for all such pies, find out what is the expected value of such thing. Only thing is that the way in which you are moving is actually being governed by the MDPs, governed by the MDP dynamics, which means that the probability transition, you are using this rewards, you are using the reward function, and pi, you are using some specific pi for a given policy. You are doing this and do it for all the possible policies. That is going to tell you that pi astic. Given all this formulation of pi and optimal such policy, we need to now understand that how can you say that given two pies, which pi is better? Because now you are ranking or probably come up with a partial ordering between multiple policies. So how you can say that which policy is better, or which policy, what is the order between different policies? So for every policy, now we are saying that we are going to have two values for every policy. We are associating two different values. First value is actually the value function, second is the Q value function. And now you understand that this Q value function is the thing that is going to play some key role, and that is why when we say that deep Q learning or deep Q learning algorithm is actually trying to learn this function. Soon we will see what it is and how it's being utilized to solve MDPs. So if I say that you have got a value function, so if I say you have got a pi, then what is the value function that with respect to a given policy pi, how good is a given state S, which mean that this pi is actually the fixed, given some fixed pi. Now we are saying that if you follow such a pi, then how good a given state is, which means that at any state how much DCFRs that you can extract if you follow this pi, and from this particular state ST. So from this state, if you keep on moving, follow a given pi, that how much or what is the maximum DCFR that you can achieve. That is the value of that state, which means that if agent just follow pi, how much DCFR is expected as the value of that state S for a given pi. Now let us see that, which means that you just have to move from a state ST following pi, get yourself terminated, and see that what is the maximum DCFR out of all possible ways or the directions in which you can go. What is the expected DCFR, maximum DCFR that you can have? Now let us see that what is this Q value function. So here when I say that at any state st, you are moving in all possible things, and then you got terminated, and then you do it for multiple times, and you will get multiple values and averaged it out, and you will get the value function with respect to pi for this state. What is this q value function mean to say? It will say that previously it was the function, value function was the at related to the state. This is q value function is related to state as well as an action, that at this state given a pi, at a certain state, if you take an action 80, then what is the maximum that you are going to get? Because if you take an action, it doesn't mean that you are going to end up at the exactly same state every time. It's a stochastic word, so you can end up at different states. So q value is one step ahead of your value function, which means to say that given a policy pi, how good is a state action pair is. So here it was how good a state is. Here it is saying how good a state comma action pair, which means that if at this state, if you take an action like this, how much DCFRs that you are expecting. So instead of directly following the policy at state S, agent first takes an action A and then follow the policy pi, and Q value for such a thing is the expected DCFR. So let us formally define both of them. Value function. So this means that following pi, for this state, what is the value function? So you can have V pi S1, V pi S2, and so on. So it is defined as I just have said, and you can see that the value is being written like this. So you all understand that what is this? This is your expected DCFRs. So you are starting given a state and a policy. If you move with respect to this policy from this state, got yourself ended, and do it for multiple times, find out the expected value. That value is actually the V pi S. Q value function. So now you can see that again the same thing, that S and A correspond at S. If you take an action A following this policy, then the Q value is going to tell you the expected maximum expected. In fact, it's not the maximum, but that's actually the expected reward, because for every pi, when pi is fixed, you take all the possible directions in which you can go from S after A and do it multiple times and find out the average. That is why you can see here that is the expected value. In Q, suppose that for this example, S is, I'm having S1, S2, S3, and for action we are having A1 and A2, two different actions. Then all these possible things can be there, and let us first understand that given a state and an action, so there are 6 different action state pairs which are possible. Assuming that S2 and O2, assuming an S2 and O2, sorry, S2 and A1, what we are going to do is that for some pi and state S2, we are talking about state S2. Okay, so that is V pi S2. What is this? That's the value function corresponding to S2 with respect to this pi, value function corresponding to S2, and that's the Q value function corresponding to S2 and A1 and S2 and A2, and then it is with respect to this pi. So which means that what is this? This is the what action that you can have at a state S2. So you can have 2 actions. So that's why it's going to tell you that what is the probability for this and what is the probability for this. That is going to be coming from some pi. And if you know the exact pi asterisk, then that is the best pi. So it is not guaranteed that this is going to give you the maximum DCFR. This is guaranteeing that this is going to give you the maximum DCFR. So out of all possible policies, you compute this, and then you can know that what is the maximum that you can get out of all the available policies. So the way in which this q pi s comma a is defined is exactly the same the way in which value function was being defined, that for given pi, if you are at a state this and take an action this, then you keep on following this pi continuously and find out that what is the DCFR, and then do it for multiple times starting from this and taking this action, keeping on both of these things fixed, but move with respect to this pi for multiple times, get yourself terminated, find out the value, add it, and find out the average value. That is the expected value, and that is going to be the how good a state action pair is. And now you can understand that what we are trying to do, we are trying to, once we have got this, and this is actually telling you that how with respect to this pi how good this action state pair is. And suppose that at that state, if you take that action, this action, and this action is no good, then the corresponding probability should not be incremented, which means that at this state I should not be taking this action. I should have to take those actions which are having more and more and more producing more and more DCFRs. One equivalent representation is that here you see that how this thing is actually being written is that, so if you can open it up, it's going to be R0, or it's going to be say RT plus RT multiplied by gamma, gamma, and so on. So now you can see that it's starting from, I guess, let me write it over here, that it's starting from RT plus gamma, sorry, RT plus gamma, RT plus 1 plus gamma square, RT plus 2, and so on. So that's your expected DCFRs, we all understand. But equivalently, you can write it like this, in which we are removing that K and we are starting from, say, at any point over here. And here we have chosen my K is going to be incremented the way we have shown here in the first part. Here, what you can do is that you just, because time is just a variable, so T is going to be equal to 0. And then at this point, what you are going to get, so we are just saying that T is, so here what you are going to get is that whenever you are starting, assume that that thing is actually T equal to 0. And here you are going to get T0 plus gamma times R, R0 plus gamma times R1 plus gamma square R2 plus, and so on. Both of these things are actually exactly equivalent, it's just the naming convention. And so now what you can see is that this is slightly more easier to write without much mess of this K. Both of them are exactly same. Exactly, this is the thing that in which we are interested to find out at any state ST. At any state ST, if I follow this pi and do it multiple times, what is the expected value that I'm going to get of my DCFR? That is my value. And at ST, if I take an action A, T, and after that I follow my pi, do it multiple times, get myself terminated, find out the expected value, that is going to tell me that Q, pi, ST, and AT. Yeah, these are the two things. And then it comes that what is the optimal value function and the optimal Q value function, because our pi is going to be dependent, pi ST is going to be dependent upon optimal Q value function or optimal value function. So both of these things can be the optimal, can or may be optimal whenever we can somehow come up with the best possible value function and the Q function. What does it mean? Very simple, that V S is equal to, over all the policies, you need to find out what is the best V pi S. So over all the policies, you need to iterate and see that what is that policy which is yielding me the maximum maximum DCFR from this state. If I follow that policy, I'm going to get that maximum value, and that is the maximum value function. What is the optimal action value function is that this is actually saying that q asterisk s comma a, which means that overall the pi's, you just need to compute this thing. Just the same way value functions are actually being defined. And if you wanted to open it up, we just have written the same value q pi a, q pi s comma a, and we just have defined that q pi f comma a is nothing but the expected DCFRs. Right. So let us see that what does it actually mean. That suppose that I am an agent and I'm at state S, and I take an action A, got a reward R, and my agent has now moved to an state S dash. So at this S dash, what are the other actions that you can take? I am saying that I can take k different actions. What are those? A1, A2, A3, A4, some A dash, and some AK. So if I take these actions, then I am actually ending up with multiple states, and whatever the states over which I am going to end up after taking this action, I am saying that from there, what does it mean that if I know my q asterisk, and that is the optimal behavior. So if this is the optimal behavior, then in between each and every behavior that I am going to get, all of them is actually going to be the optimal behavior. So that is what we are saying, that at S, if I take an action A, reach to somewhere, then what does this mean is that q asterisk at S dash, if I take an action A1. So we are defining things over here. What we are interested in, we wanted to know that q asterisk S comma A. But to compute this, we are breaking it into some optimal recurrence, which is saying that at S dash, what is the best that you can achieve if you take A1 from S dash? What is the best that you can achieve if I take A2? What is the best that I can achieve if I take A dash or AK? So out of the best, I take the again the best. So out from this path, what is the best? This path, what is the best? This path, what is the best? And this path, what is the best? I will choose the one that is going to give me the best, and that is going to be the solution or the answer for this guy. But for here, if I wanted to choose what is the best, then S dash A1, S dash A2. So that is why S dash A1, because once I take this action, what is the best DCFR that I can get? From S dash, what if I take A2, what is the best that I can get? And in this way, you can see that first I am going to get this R over here. Yes, because from here I am going here. So that is why I'm going to get one reward, that is R. That's why I have written this R. And then gamma times that R. Why? Because that's going to be discounted, and I need to see that which one is the best. Assuming that, suppose that this is the best. Just I'm assuming that this path is going to give me the best thing. If that is the case, let me write it, that max of all possible paths which are possible. And what are they? Q asterisk S dash A1, Q asterisk S dash A2, Q asterisk S dash AK. And out of all of them, whatever is the maximum, I am assuming this one. So that is why Q asterisk S comma A is going to be R plus gamma times Q asterisk S dash A dash. Now you see that from here, what you have got, it is actually that I need to find out this value. Instead of getting a solution directly for this, I have got a solution which is actually in terms of another problem. And that is why we have divided this big problem maybe into some another problem. And this is actually not divide and conquer. This is actually dynamic programming, because the problems that we have, I wanted to solve, I divided into some smaller problem. And these problems, if these divided problems are independent, then this is divide and conquer. But these problems are not independent, because when you are solving this, it is not the case that, you know, the same thing is, you know, there is some dependence. You wanted to solve this and this thing, both of them are actually dependent over each other. If problems are interdependent, then the solution is actually dynamic programming. If they are, you know, completely independent to each other, then it can be seen as a divide and conquer. So the good thing about such a thing is that both of these optimal solutions, or the optimal values, q astic or the v astic, both of them are actually both of these things are actually following the Bellman optimality condition. And this is actually the Bellman optimality condition, that you can see that these values are using the previously available um, best values, and your upcoming solutions are going to be dependent upon the previously sorted out optimal values. Yes, so here now you can see that and one more thing, that at any state, if you take an action, that you are going to land up in that s dash state, but that is not a fixed state, but basically coming from a probability distribution, which means that at s state, if I take an action a, then probably you may end up with in s1 with this probability, s2 with this probability, and s3 with this probability, which mean that if you wanted to find out the q astic s comma a function, and that is the optimal function, what is the best, how good is this state and action pair under the all possible pies, or all possible policy, is that you need to find out the expected value over all those s's, over which after taking after taking a over s, my agent can go. So my agent can go up to s1 or s2 or s3 or all different things, and all of them are actually you know, combined into one set, and that is actually, we are saying that epsilon state. So it may reach to any set of, or you know, some set of states when it take when at state s I am taking an action a. So we need to find out the expected value of what? So we just have seen that what we have done over here, what is the immediate reward plus the discounted reward, but maximum value if you take you know, all, if you consider all the actions from the state where you have reached after taking an action at state s, right? So that is why we have written over here that it may reach to all possible, you know, different possible states. For all these states, what we need to do is that first find out that what is the immediate reward plus gamma times you need to maximize. So find out that all possible actions in which you can for all possible actions that you can take, and for all of them you are taking that q astic, and for a given s comma a. So the same thing we just have written over here. It is much more generalized, that for all those s dash, you know, s dash, for all the actions that you can take, and find out the maximum q astic out of that, add, and that is the expected value that we are actually looking for. So so both of these things, q astic and v astic, both functions actually satisfy this Bellman equation and are actually being defined recursively. Yes, so till now let us see that if you have any questions, then you can ask in between. Do you have any question? I guess that you'll have to unmute first. All of them are muted. Yes, Preeti, you have any question?
No, sir.
It was follow. You was able to follow, or
Yes, sir. I was able to follow, but I will again see your video in YouTube again, sir.
yes. So okay.
This video again I'll see it. Yes.
Okay, fine. So let me go. Now the point is that what the problem that you may face is that we have used the Bellman equation and the Bellman optimality thing,
Yes, sir.
and because of, and that is actually solving the thing in the form of DP. So let us talk about one basic DP. So now you can mute yourself. So in 5 or 8 minutes we will finish this, and then then probably in the next lecture we'll talk about something else. So the point is that what happened in that q-astic equation, what happened in that q-astic equation was something related to the Bellman optimality. So we need to understand that that if you wanted to find out the optimal solution q-astic s comma a, then it is nothing but you can decompose this thing into small things, and all these small things need to be optimal on its own, and that is the optimality condition that's being used, and the recurrence got set up, and we keep on solving those recurrences. So how such a recurrence is being developed or being represented, we are going to see this Bellman Ford shortest path algorithm, which is very, very easy. Those I Yes, any
Sir,
question?
one doubt is, sir, if we are doing dynamic programming to solve it, then there is no learning, no, sir. Definitely will give the high optimal reward, right?
Yes, that is correct. So we are first trying to understand that if we are able to apply DP, then we will apply DP, but later you will see that our states are exponentially high. So DP cannot be applied, but we need to figure out the Q asterisk somehow. Then instead of using exact solution using DP to come up with the Q asterisk, we take a neural network which will approximate the Q asterisk function.
Okay. Okay, sir.
Yeah, so that we will see. But first we need to understand that using DP, how such a thing can be possible. Similar things are going to be applied, but instead of trying to solve it for each and every state and coming up with the solution, that is not being possible, we employ a deep neural network to learn Q asterisk function for you. Yes,
Okay. Okay, sir.
fine. So first let us understand this Bellman Ford shortest path algorithm, in which you all understand that why we have applied Bellman Ford is that, and those who are not, I mean, please understand that's a very important algorithm, which means to say that Dijkstra is not able to be deal with negative weights. So if you have negative weights, then you need to apply Bellman Ford, and if you have negative cycles, they are anyways not allowed when you are talking about the shortest path algorithm. Our observation is that given any graph v comma e, any graph that is given v comma e, which is having no negative cycles, then there exists a shortest path between s to t, that is a. Simple. Why? There should not be any repetition, because if there is any repetition like this cannot be a shortest path, because if this is the shortest path, then you are going to have cycles. So there cannot be any cycle in any shortest path, because we just simply remove that cycle from here. You start and you are having a cycle, you are ending up over here, so why you are going into the cycle? So that's cannot be a shortest path. So shortest path need to be simple path. Secondly, if it's a simple path, no repetition, then what is the maximum number of edges that you can have? So if nodes cannot be repeated, then total number of nodes are this many number of vertices that you are having, then at most these many number of edges that you can have. You cannot have more than n minus 1 edges, possible edges, if your n is the number of nodes that you can have. That's that's actually an observation, and that observation is actually being used to set up the recurrence for you. I'm just trying to show this recurrence so as to let us understand that how such recurrence relationships are actually being set up, and that will help you to really understand that how that q-astic thing was being set up. So from any node v, where we are going towards the t. So that is the thing that we are looking for. Right now we are saying that from source we are going to some target node, Instead of this source, I am saying that suppose that I'm going from V node to a T node and I'm following certain path, some path I'm following. So from V, I first have gone to W, and there can be multiple different Ws, because from V, whatever the adjacent nodes which are being there, they all can be. Right now, I am choosing one such W. So there is a cost associated to this edge, that is C, B, comma W. This cost is saying that, well, um, the cost associated if I choose this path or this action, if I say. Now the point is that I have defined my opt I comma V. Opt of I comma V, what does it mean? Opt of I comma means that V comma means that I am representing the minimum cost of, say, path P from V to T. V to T. What is the meaning of this? V comma I comma V. That if I go from V to T, what is the minimum amount or the minimum cost if I use only K edges? I'm going from V to T. What is the minimum cost if I use only I edges? Because here there are negative edges. Because there are negative edges, if I keep on adding more and more edges, that from V to T, if from V to T, what does this mean? If I use only 5 edges, and if I use only 6 edges, so if I add more and more edges, it may possible that my minimum cost keep on decreasing, because I am having negative edges in my graph. So if I add more edges, it may be that some negative edge got into my shortest path, and because of that I started to get better path. So which means that from V I am going to T and using only I edges, then that is opt I comma V, which essentially mean that from V to T, if you go using only 5 edges, it is definitely going to be more than from V to T if you go using only 6 edges, because here you are having one more edge. And if suppose that one more edge is having some value which is negative, or with this 6 you may got a better path, so that it may happen, and it's definitely going to happen in several cases. Because of that, if you keep on increasing more and more edges, possible edges in between, from going from V to T, you are going to get better and better paths. So here, what does the meaning of opt I minus 1 comma W, which means that W to T I am going using only I minus 1 edges. I am going from W and reaching to T using only I minus 1 edges, and when edge I am having over here. So this doesn't, this mean that from W, what is the best cost that I can get using only I minus 1 edge? And now you can see that if I wanted to somehow figure out that what is the opt of I comma V, which means that from V I need to go to T using only I things, I edges. This mean that either I am going to be, so I comma V is saying that either it is going to be equal to opt of I minus 1 V. This means that either I am not using that new edge, whatever I know using I minus 1, that is actually the minimum that I am having, or I am using this. If you are using, then if you use that, then what is the final cost from V to T? From here to T, the minimum cost is this, and you are using this, so that's why CVW you have added. So if you use that cost, then CVW plus this thing, you are going to say that that is the best or the opt of V comma T. So this is one thing. Or you will say that I know that opt of I minus 1 comma V, probably either that is good, or using this new and then using I minus 1 from here. So one edge over here and I minus 1 edges over here. So now you can see that if I see that from V I am going and I'm allowed to take I steps or I edges. One is that what if I use I minus 1 edges, and what if I use I edges? If you use I edges, then W I minus 1 opt of that plus the cost associated. Or if you are not using this, or basically saying that at most I minus 1 edge, that is going to give me the answer, then this is the second thing. Out of this, which one is the maximum we are going to choose? Because these are the two only available options. Out of that, whatever the option that I can choose, the option that I'm going to choose is the one which is going to give me the minimum value. That is the shortest path. So from V, as I have said, that one W we have chosen, but it may be the case that there are multiple W's, W1, W2, W3, W4, and all possible W's. And from any Wi, if I want to go to my T, then you can understand that opt of W4, I minus 1 is telling that best possible path from here to here, best possible path from here to here is the opt of W3, I minus 1, and so on. And the cost associated from V to reaching to W4 is, say, V, C, V, W4, W2, and so on. Then this is the final optimal value that you can have, I comma V. That is the minimum of either this thing when you are not using at all this new edge or one more edge. So if you are only using I minus 1, it may be the case that new edge addition is not going to be helpful. So that is the previously hold solution, or minimum for all possible adjacent nodes of my V, all the adjacent nodes of my V. And what we are doing, that we are just adding from W for that node. If I go to T using only I minus 1 things and adding the corresponding cost, that is the minimum. That is actually the DP of your Bellman Ford shortest path algorithm. Exactly same thing is happening in the case of Q value function, Q asterisk value function. What is it saying? Suppose that if I'm at node this, and from this node where I wanted to go over here, I wanted to go. So you can go to different places, choosing different actions depending upon your state, and choosing different action. You may end up at different other places, and from there, in this case, you are going to one state. In the case of Q asterisk, you are going to multiple different stages where you can get yourself ended because of your termination termination state. So multiple states can actually be there over which you can get yourself terminated. What you want to know is that what is the best possible DCFR from any state. So that is your best possible DCFR for this, best possible DCFR for this, and so on. So that is why you can see that it is saying, this is saying that from this node, what is the best path using I minus 1. In the case of Q asterisk, you will see the same thing exactly. This is saying that from this, if I go to this state, what is the best if I take A1? What is the best if I take A2? What is the best if I take A3? And out of that, what is the best? So that is why max of all of these optimal things, that is going to be there. So that is the DP, and that is why I explained shortest path for you. Yes, so we are done for today. If you wanted to ask any question, then please ask.
Sir, in that Bellman Ford algorithm, sir, where you said where will Q star come into that place? Here, the neural network that
Yes.
you are talking about, in which stage will it come, sir? Like, is it learning will happen in each of these nodes? I mean, while
Yes,
implementing.
yes, that is good. So I understand that you wanted to somehow understand that how deep networks are. So that is actually deep RL. Right now I'm talking about the basic RL.
Okay.
When we understand that that what is going to happen for this algorithm, suppose that this deep this Bellman Ford algorithm. So for this, for each and every node you need to do that. And for how many nodes which are there, so you will say that some n nodes, and suppose that this n is exponentially high, then you need to do it for each and every node, and for each and every node, for each and every action. So first we will have to understand that what is the complexity of such algorithms, and such dynamic programming algorithms are useful because we can reuse the previously computed values. These values can actually be recomputed multiple times. But and that is why memorizing of recursion is going to happen in the case of DP. But the point here is that suppose that these nodes themselves are very high, then you cannot systematically apply this DP for each and every node. And if you cannot apply DP for each and every node, then you cannot exactly get this Q is critics. Then what we will say is that since we cannot get this, I employ some deep neural network to somehow learn a function which is being represented by this Q asterisk. Q asterisk is a function. It's a black box parameterized over theta, and this theta is going to be learned by this deep neural network. Yeah, so we will formalize again that problem of learning into that DNN, but first we are formalizing the whole thing in the form of MDP, and that MDP solution in the form of pi, then the solution in the form of Q pi's, and then how we can iteratively solve to get these Q pi's. And yes, that is actually iteratively we are solving. First we solve OPT for 1, then we will 1 comma all nodes, and then we will solve for if I take 2, if I am allowed to take 2 nodes and going from V to T, and then if I am allowed to take 3 nodes and going from V to T, and keep on doing, and ultimately you are going to actually solve the problem when you have got the when you have got the solution, which is like this, that from S you are going to T and only n minus 1 edges that you can take. And that is the observation we have seen for the Bellman Ford, that it cannot have more than this. The same thing is going to happen in the case of Q asterisk. First we do it for some random policy, and then we somehow got another policy which is slightly better than this random policy, and then we keep on refining. So we will so we will take a policy, and then we evaluate that policy, and then we improve that policy, and we keep on doing this thing in loop, and keep on refining, so that at some point of time when your Q function or the Q asterisk for your Q function is not changing, which essentially mean that your Q actually have converged into some Q asterisk function. Certain proofs are also available that they show that such functions are existing, must exist, and such a DP sort of solution need to converge over there. Yes. Any other question?
No, sir.
No. Yes. So what we'll do that we will upload these things, and I request all of you to please understand it once again, because everything is going to be dependent upon whatever I have discussed today, and things are going to be slightly more messy. So if you understand this stuff, in the next lecture we can discuss once more about few of these things, and then probably we will started to explore more about policies, and given different policies, how we can evaluate a policy, how we can improve a policy, and then how we can learn a policy, and then deep Q learning. These are the stages that we require to reach up to deep Q learning. Yes, thank you. Okay.